You've seen this already. I'm not going to go through it again, right? So, but this is the process. You need to imagine we have our samples, we went through the process, and we got our FASTQ. I mentioned this before. Oops. So this is the steps we're going to be taking today and tomorrow to analyze our data. We have the samples. We're going to do QC and some filtering. We're going to use a splice aligner to align our reads to the human genome. We're going to do quantification. Actually, these 3 steps, we'll do them this afternoon. And tomorrow, we'll focus on differential gene expression analysis. And depending on time, we may do some downstream analysis. So for every step, you're going to be using different software. We already seen FastQC. For filtering, we're going to use FastP. And this is the files you're going to use as an input, right? And every step, you're going to get a different type of file. And it's going to be evolving to our final results table. As an aligners, you find different options. Probably the 2 most popular ones are called HiSide2 and STAR, but there are others available. The one we're going to be using is HiSide2. To be able to do alignments, we're going to need our genome, which is going to be in a format of FASTA file, FASTA. Sorry, I call it FASTA, but actually the name is FASTA. You've seen that format before, where we're going to be storing the genome. We also need another file called GTF. GTF are the annotations for that genome, and we'll see that how it looks like a bit later. And when we do the alignment process, we're going to get a file called BAM, right? And some of you are already familiar with it. It's where we store our alignments. And all of those are different formats. When we do quantification, there are different tools available. We're going to use one that is called a string tie, and it basically gets the alignment and converts those reads mapping to genes into counts. So if we see a read mapping in X gene, I'm going to get a count of 1, and so on, and so on, and so on. So you get what we call a count table, matrix of counts, or count matrix. It has different names, but we get a table with the counts. So genes are going to be rows, and the samples are going to be columns, and we get the counts. Now, for differential gene expression analysis, you also have a lot of options. R is very popular, and there are a lot of tools in R or libraries in R that you can use. You have DSeq2, RSEM, or HR. The one we're going to be using is DSeq2. Basically, it takes the counts. Actually, if you want, you can skip the spot of creating normalized counts, but it's something that you need to do through this process, and we'll talk about it. And at the end, you get your genes being differentially expressed in some sort of table with the fold changes, p-values, q-values, and so on. With this, if you want, you can do all other analysis, right? And it's where we get the most common one would be a pathway analysis, and there are a lot of tools available, amazingly a number of tools available, and even websites where you can just upload your data there and do the analysis. Some of them are David, Gorilla, Ingenuity Pathway Analysis is a commercial one, and so on. There are plenty of them. But again, our steps are going to be today. So the QC and filtering, we're going to use FastQC, FastP. We align with HiSide2. We're going to use string tie to get the table. And tomorrow we're going to use DSeq2, and we'll see what happens with the pathway analysis depending on time. We talk about the FastQ, so I'm not going to go through this. You already know this. So what are the goals? So remove the low quality, the FastP. So for HiSide2, so alignment. We said we need 2 pieces of information, right? We said we need the FASTA, where we store our sequences of the genome, where we're going to be mapping our reads. And we need the annotation table. You can do it without the annotation table, to some extent, right? And try to do discovery of transcripts. But if you have it, you're going to get better information, right? So this is the annotations of the human genome, and stored in a tabulated table. I know it looks quite complex, but you remember the batch file, right? Same idea. You get a chromosome, starting an end position, and it tells you what is in there. It's an exon. And then you have, later on, you're going to have what gene belongs to, the transcript ID that belongs to, and so on and so on. So this is how it looks like, the table. You don't need to know many details, but this is a way we have to store the models, or you call it the gene annotation. Yep.
Is it like the SAM file or map of the variant calling thing? No, you're confusing between genomics and transcriptomics. Yeah, this is I understand.
Yeah.
Yeah, but so is it similar to this?
To a GB, sorry, a BCF file? No, no, it's not. Similarities with it? No, no. I mean, all of them look alike in the sense that you're going to have some positional information, right? Chromosome. Yeah, this is basically annotations. That's how we store annotations. They have different extensions or names depending on the version, GTF or GFF. But that's the idea. This is how we annotate coordinates for something. We assign some sort of feature like an exon, a CDS, or it can be anything actually, right? And then what it belongs to. So that's the most important information, right? We know that if a read maps here, we know the CHIT1 is the gene that produced that read. Okay, the alignment, right? So we use the genome information. That's where we're going to be aligning our reads. We have the GTF information or the GTF file who tell us what is in every position on that genome. And now we need to align the reads. So in this case, we're going to use the splice-aware aligner HiSat2. So what it means is that when you have situations where a read maps a portion of an exon and then the same read maps later on in a portion of another exon, right? So you need an aligner who is able to detect these situations. If you use a classical aligner, it's not going to be able to map this, or it's only going to map the first fragment and not the rest. So that is why we use this type of aligners, the splice-aware aligners. And the way they work, generally they find a seed and they try to extend if it doesn't map because it has the information, right? It's able to build, okay, I have a read that maps at the end of this gene. Let me look at at the end of an exon, let me look at what is the other exon and see if I'm able to map the rest of the read. Out of these, we're going to obtain the BAM files. As I mentioned at the beginning of the workshop, I told you that we'll talk about the formats. I think you need to be aware of the formats and how they look like, because even sometimes we visualize them minimally to know whether it's in there. This is what is called a SAM alignment or SAM file or BAM file, depending if it's compressed, or CRAM if even you compress it even more. But it's the same structure inside. I don't know if I should go into details, but if you want, we can go a little bit. But the main idea is this is your gene ID. You remember the FASTQ, gene ID, the read ID. In the FASTQ file, you have that long name. So you have it here again. You have the chromosome and position where it aligns. Also, you have some sort of mapping score. Remember we talked about this? So 0 is terrible, right? 0 means it maps in multiple places or in no place. This thing here is what we call the cigar string. It tells you how it maps. It is quite convoluted, but if you look at the first one, M means matching, D means deletion. So you have 33 bases matching, 3 deleted, 21 matching, 3 deleted, 47 matching. And that should be the total length of the read. So a perfect match is this one, 101, right? Still, it probably maps in multiple places.
So 0 means it's mapping to multiple places?
Probably, or nowhere. I think you use 0 also for nowhere.
When there is some number like 28, what does it indicate?
28 probably means similarly, or in this case that you have an S. S means for soft clipping. So 61 bases doesn't map only 40. So that is suspiciously rare, right? So it could be from mapping multiple places or because there are 61 bases not mapping anywhere. So another thing, the read is also represented again, and the quality scores are stored again. So I think we talked about this at the beginning. There are other ways to store your FASTQ files. It could be stored in a BAM file if you want to. So from the BAM file, you could go back to the FASTQ. BAM file can have, by the way, multiple columns, and sometimes you can have really long columns where you store your annotation. I know some people here use variant calling, so there are columns specific to store annotations and other stuff. No, you see I got confused. That's the BCF file. Like, you don't store annotation here. A typical tool to manipulate BAM files is called SAMtools, and we're going to use it also today. Probably if you work with alignments, you know SAMtools for sure, because it's the most common one.
If we make a FASTQ again from a BAM,
yep.
will the order of the reads be the same, or it will be jumbled up to go compared to original FASTQ? If you
Yep.
convert it first to BAM, and then you try to make a FASTQ file from that BAM,
Yep.
will it be the same order as the original
No. It would be different order, probably because this has been ordered by chromosome and position, so it's going to be different. There are ways also in the sum format. You also store if it's read one and read two, so you have ways to split them to create read one and read two. Also, there are tools to split them.
I have a question actually. So, if you have not sorted the BAM file, still it will actually come according to protocol, because actually if it is not sorted BAM file,
Yeah.
initial alignment comes without a sorting.
Oh, that's a good
Does that
question.
follow the read order or is still order the sorted order?
I don't know. It could be, generally we sort them by name or by position, so I'm not sure.
The chromosomal. Yeah,
I never try.
Sorted BAM, I know that is based on the chromosomal position, but then what happens to the raw unsorted BAM files?
I don't know. Maybe it is, I'm not sure. But it's generally not a problem, right? You don't care how the FASTQ file is sorted or not. Meanwhile, you're able to recover them. Read one always matching read two in the position, right?
Some packages, a BAM conductor package which uses BAM files, which do chip-seq analysis and that kind of thing, they want sorted BAM file.
Oh, yeah, no, that's common. I mean, a lot of softwares, they want sorted and indexed, yeah. Yeah, that's something that I don't know if I'm going to talk here, maybe later. So, because these files are so big, we create indices. So, like a book. So, we index the book, so when we need to access the file, we are able to access quickly the position of one read, or a position of chromosome 8, position X. So, to be able to go quickly to that, we create an index of that file. And that's common. Everything that is too big, like BAM files, we index them. BCF files are indexed to. Sometimes we use some tools to index for quick access. And a lot of softwares, they want you to sort the file and also to index the file. Oh, there is one column that I didn't explain, right? I think it's, this one here. So this is a sum flag. I think we call it sum flag. It's a flag. It's a way to store if it, by a number, is a way to store if it's read one, read two, if it aligns to the positive or negative strand, if the partner, read two, is aligning or not. I mean, impossible to tell what it means by a number, but there's ways you can even check it if you want to. Okay, so quantification. So now we have our alignments in the BAM format. So the different options. I don't know if you've done this before. Feature count is pretty popular, or HTC count is another one that is popular. We're going to be using string type. And basically what we're doing is start counting, right? GNA, how many times we see for sample one, et cetera, et cetera. So we get what we call the row counts. So this is the typical file we're going to use tomorrow to do the analysis. So what we want to do today is to reach this point, from the FASTQ files to a table with counts. And of course, we can talk about this, but basically, you probably can assume you cannot do an analysis directly with the row counts, compare samples, because each sample can have a different number of reads, right? So we need to normalize them, and we'll talk about this later. For differential gene expression analysis, that's for tomorrow. I'll show you Galaxy before, but everything, I think I mentioned also yesterday, but everything we do, you could do it in Galaxy, right? If you don't want to do command line and you want some generic analysis, Galaxy is your friend. And if you don't have many samples, because it's super slow. Parted flow is the other one that I mentioned, right? Okay, so I think we are almost ready. So we're going to do these 3 steps. You know the trick.
But I think you can retrieve the
Sorry.
FASTQ file in BAM without any changes, because in one of my projects I submitted my old files to NCBM, and one of my file got corrupted, and they said that your FASTQ file is corrupted. And then I searched on my system and genome station, I couldn't find my original FASTQ file or FASTQGZ format. And then said that you can just give us the BAM file, we will sort it out. So there are some tools that you can sort it out the BAM file by using the query name exactly. You can retrieve the FASTQ file from BAM file, and that's why I submitted the FASTQ BAM file, and from where they retrieved the FASTQ file, and then my project got the accession ID.
Oh, you're already connected, right? We didn't disconnect anything, so you're already there. So you don't need time. You can go straight to do the exercise. You probably have a view similar to this. You've been doing all this through this morning. So our exercises today are in day 2, FastQ2 counts. So you can open that folder. And you have a Jupyter notebook that is called FastQ2 counts step by step. You can double click. And you're going to see something like this. I know yesterday I went really quickly to this, so I'm going to insist a little bit more today. So like any other document that I've been putting together for this, it has the same type of format, right? You have some text that it tells you what you need to do. You can run them. At some point, you're going to see the street light. That means you need to or change the code or type something, right? Any questions about, so you remember what it does, right? So I mentioned yesterday that for this exercise, you can use the terminal directly. So you can type these commands here in the terminal, and you would get the same results. Or you can execute the Jupyter notebook step by step if you don't feel comfortable with the terminal. And you should get exactly the same results. This is a Python notebook, but we are cheating and utilizing this. Can you read the screen, or it's too small? From the back? Small? It's better? Okay. So you're going to see this on top of every cell. It's basically telling we are not executing Python. We're using the bash commands or using terminal commands. So that's what it means. What I'm trying to teach in this first cell is basically, this is how we define the variables in bash, very similar to R, right? There's not much difference. Echo is just printing. So basically it tells you what it does, right? So you don't have to wait for me if you want to execute it. Any questions on how the variables work in bash? There's an issue, though, that in Jupyter notebooks, they are not designed for bash, right? And every time you execute a cell, if you define a variable 10 cells above or 1 cell prior, you need to define it again. It's not like R that knows that a variable is defined. In here, because this is not designed for bash, you need to define it again every time you use it. So how we run commands in the terminal, I explained that the other day too, or yesterday. You generally open the terminal, navigate to the program, what it is, type the name of the program, and you execute it. Generally, I believe it's similar than we did with R, right? When you execute a program, in R you execute a function, you give him arguments, or we call it arguments or parameters, right, for that program. So it's the same idea. So this is just one program with a few parameters after it. So just a couple of examples. Those are just listing files, right? Or giving some parameters to it, and it do something different. The same command, depending on the number of arguments or the type of argument that you give it, you're going to have a different behavior, right? So here I'm just listing the files. Here I'm listing the files and giving some colors to some of them, right? I was mentioning, generally, this is quite common that you can use arguments with 1 dash or 2 dashes. It's not a hard rule, but generally 1 dash, the argument means that you're only going to have 1 letter after it. If you use 2 dashes, you're going to use a full word, right? And that's what we see here. 1 dash for a single letter parameter, or 2 dashes if you're giving the full name. So of course, you're going to have a different list of files, right, when you do it. You're not going to have maybe you're going to have the same ones, but the columns are going to be slightly different. I don't know if I should stop here for a second and explain what it means. Any interest? Yes? Okay. So basically what I ask is to give me as much information as you can about the files and folders, right? Color in this case means this is going to be directory or folder. That's why you have a D here in front. The ones that don't have color are just files. These are permissions of the file. So who can read, that's the R, who can write the file, and who can execute a file or navigate through it. So in this case, are my files. I'm the owner. So the only one, so let me explain this a bit better. So the first digit, it tells you if it's a file or is a directory. The next three, or groups of three, give permissions to that file. In this case, are divided between reading, writing, and executing. I don't have, yeah, I have an executing here, right? So X means execute, read means, R means read, W means writing. So in the first case, the first three numbers indicates the owner of the file has those permissions. The next three letters, is the group. Whoever belongs to the same group can do that things. And the last one is for the other people. So this is the way we control who can read this file. So this is the owner of the file, which is me, and this is the group, which is my group. So if you go to my folder, you're not going to be able to do anything with it, except maybe navigating through these folders. That's what it means. This is the file size in non-readable way. It's not nice, but it's bytes, right? The time of creation or modification, and the file name. Yep. All this is not important for what we're going to do today, but I think it's probably good if you know those things. I think I explained this too, but the basic idea is the same way that in R, if you don't know how to do something, how you can get help. I would tell you, basically use Google, right? The program that we saw before called HiSat2, you don't know how to run it, Google HiSat2, and you're going to get the documentation. I think it's your best shot. But there are other methods, right? You can use the manual for LS. So if you run the first one, you're going to get a long manual provided by the system. It is hard to read. So I think Google is a better option in that case. Oh, by the way, let me close this. So I think you saw this at some point, but if you don't want to see the full content, if you click here, it's going to extend the window. You can hide it a little bit, but if you touch the blue thing, the blue bar on the left, it would hide it completely. So if you think it's occupying too much space in the document, you could hide it. I think another important thing you need to know about Bash, it is, you notice that we execute ls, and it's not in our folder. ls is a program that lists the content, but it's not in our folder. How knows the system where to look for ls, right? So there is a variable called path in our system that the OS is the first thing that it reads. It tells me, so let me explain again. So path contains a lot of folders in it, or a bunch of folders in it. So when you start your system, the system reads the path. It contains a lot of folders, so it tells me every time you try to execute something, I'm going to look inside of the path variable and see if I find it. If I find it, I'd execute it. If not, I give you an error. And again, you can try, right? So we can give a try if you want. So if we try to execute ls, we already seen that it finds the program, right? If I try to execute HiSat2, it's not in our folder, right? It finds it. Oh, sorry. No, again, you see? I need to do the trick. It finds it. It's not in our folder either, right? So what if I do star aligner? I don't know if it's uppercase or not, but it's an aligner. What is going to happen? It's going to tell me some error because I don't find it. It's not in our system. So try to print path. Right? Remember, echo is the equivalent in R for print. It gives you a bunch of names of things and a colon, another folder, a colon. So these are folders separated by colons. So these are the three folders when you start your system that the system tries to look for whatever you try to run, right? ls, it's probably in user bean or bean is where ls it is, right? So a way to know what it is, I think I put it upstairs here, right? So if you ask which ls, it will tell you what it is located in the system. So it's in bin ls. So it means bin ls must be in our path. Sorry. So bin, so you have user bin and bin, so it must be there, right? So it is in our path. You could modify path if you want to, and add more folders if you need to, but you don't have to, but you could. But if you work in your system and you want to add, I don't know, you create a program or whatever, you could add it to your path variable if you want to. But to store it, you need to modify a specific file. Right? So you could modify the file, adding more directories, your variable path, adding more directories. You need to use the export function, and you would get a new path variable. You see that I run ls again, but all of a sudden, when I run ls, I run it in the same folder, right? So I have day 1, day 2. This is the original folder that we have. Sorry, not the same one, but the same. But all of a sudden, we have a bunch of files that I didn't see before. This one that starts with a dot are hidden files. I use for the, generally, you don't need to touch them for anything. Generally, it's the OS that use them for something. So, but there is one that is called .bashrc. That is where you're going to tweak the path variable if you want the system to know it. Again, we are not going to do this. I'm just teaching some basic stuff that I think you may need in the future if you start working with different programs and things like that. So the main question is how we create the path in our system. So Conda takes care of it. So how Conda works is, remember I talked about the environments? That creates an environment, for example, for RNA-seq. You have all the tools there. You activate it. The moment you activate that environment, Conda takes the path and modifies the path to add all the folders where you have all the programs for RNA-seq. When you deactivate that environment, Conda takes the path and modifies it. So that's a trick that Conda uses to create environments. So in that way, you can have different Conda environments, activate them or not, and what Conda does is modify the path variable, right? In our case, we only have one environment, which is activated every time you connect. So there's not much trick, but you can have a lot of environments with different programs. So if you install Jupyter Notebooks and you want to do different type of experiments, I recommend you to create those Conda environments. Questions so far before we start? We got an idea how Bash works, how the programs are used. So if sometimes you say, oh, I'm running HiSat2 and I don't see HiSat, it doesn't work. Be sure you got it in the correct, well, HiSat2 it's available, but you could check it's a program that is available or not in your system. Ask which, for example, if you want to know what it is. Okay, should we start? First exercise. We've done this before. We talk about some of the things that you see here. Before you run it, can you guess what is going to happen here? We talk about head multiple times. Head is a common function in Bash, R, Python. You're going to get the top number of lines, right? It depends on R, I think, is the top 6. In Bash is the top 10. So basically, we are uncompressing and printing this file, piping it to head. So we're going to get, did you run it? Right? We get the top 10 lines of our FASTQ file. And remember that this is what I said, I think, yesterday too, that all our samples are stored in the same type of system, which is a folder per sample, an unaligned folder, and the read1 and read2 inside of it. And if you want to look how it looks like in your browser, so sample 1, unaligned, and we have the folders, the samples over there. Okay, should we run FastQC for our first samples? You run them? Okay, FastQC is going to produce the output, whatever the file it is, the original file you're running it is. And if you notice, we give them the name of the program, and the only Only argument that it takes is the file. That's the only thing you need to give it. The name of the program and where is the file. If you want, we can go and check how it looks like. The cool thing about Jupyter Labs is if you click in an HTML file where the report is, it opens it easily, right? Check the QC and tell me if you see anything wrong. Should we accept the file as it is? Is this the first? Yeah. Yep. So this is the first warning we get, right? We always said that is context dependent. So this is generally, as far as I know, is produced by the random examiners that are used to amplify our libraries. So they use random examiners to attach to the RNA to produce the cDNA. So they are not so random, and that's a problem. Well, the problem for this plot, not for our analysis. It's not a big deal if it's there.
Overrepresented sequences.
Yep, let's look at it, right? Oh, doesn't accept the no, it doesn't like it, huh? So anybody wants to make more comments? Like here that said we should check the overrepresented sequences. I mean, poly A, I don't know what it is. It could be nothing, right? A bunch of C's and T's. We are not going to do anything with them. This is not that uncommon. Bonnie was talking, it's part of the process of library preparation. They use adapters. So most probably this comes from having a very short fragment. You sequence a very short fragment. So when the sequence the fragment and then continues and sequence the adapter, which is next to it. We could trim it off. It's telling us that only 390. That's not that much, but it's what it is. Part of the trimming process, we could remove those, definitely. And I don't know if it's visible here a little bit, right? Universal adapters, Illumina, you can see them that you have some short fragments that after 40 bases, you start having the adapter present. Yes, any questions about the FastQC? We've seen them already 3 times. I guess you're bored about them already. No?
This is per base sequence content. You have told that if the GC content.
Yeah? Sorry.
So
Yes.
what does it indicate the sequences in this region?
So if it was completely random, it would be flat, right? If it was a representation of the genome, it doesn't matter what position of your read it is, it should be the same, right? But what it's telling you is it is not that representative. There are some sequences here that are constant, that don't represent the genome. And this is produced by the N6, what we don't, random examiners that are used for the cDNA process preparation. Which is,
so
again,
these are the
normal.
constant sequences, which will not be
Yeah, it seems that align always, the random examiners, it seems, so the transcript always gets, so the examiner always gets in the same position, so it seems they are not that random. One thing that you probably noticed, did you open the sample, the R2? I think we mentioned that the quality of R2 is a bit worse than quality of R1. It drops earlier. And that is because the cycles of, so in Illumina they call it cycles of sequencing. The quality drops at the end. The longer you keep running it, it keeps dropping. I mean, nowadays the quality is excellent, but
What is the ideal number?
this is all data, so nowadays you don't have to worry much. I mean, I don't know how much you can push them nowadays. 2 by 150, it's pretty normal, and the quality is great.
Over here, quality is very bad at 76 base pairs, those two cells.
Yes. Now
So
we are in sample 2. So
it
either
means
we can remove this nucleotides, that part from that sequence, trim it basically, trimming हमने जो sequence.
Okay? So are you guys doing the next step, running the FastQC for sample 2?
Yes.
Don't go ahead.
नहीं, sample 2 था. We have done only for sample 1 का R1 R2 था.
अच्छा
So I don't want you to get confused. There's 2 FastQ files, I think, in the original folder. Ignore them from now. We are working with sample 1 and sample 2 only.
क्या कह रहे? ये यहाँ पे मैंने इसको वो करके देख रही हूँ. जैसे यहाँ पे हमने sample 2. So I'm getting no such file or direct.
Okay. You made a mistake.
Yes.
inside that underline वो folders में जाके
Okay.
underline में and then उसके अंदर करी है HTML files के.
And just to, anyway, if you prefer to work with the terminal, you can still do it. So you can run the same commands from the terminal. It's the same thing. So if I want to run FastQC for sample 2, I could do it in the terminal too, and it's sample 2, on a line, right? And it runs in the terminal, same thing.
नहीं वो किया मैंने. Dash डाला. ये dash repeat the process for sample 2. कि मैंने एक कर लिया.
Actually I'm not getting that those files are getting saved in that folder, not in.
Sorry.
So I have run, this is 10 lines of FastQ file, right? If I need to get.
Yep.
So I have used.
No, but you don't need to do this.
Okay, so just run the.
No, okay. So you're doing the first exercise, right? So if you go up, so why everybody has it the other way around? We run the FastQC for this file, right?
Yes.
So this is the folder sample 1,
Yes.
subfolder analyze, and this
Yes.
is the file.
Yes.
Now what I want you to do in this exercise, the one here, is repeat the same thing for sample 2.
Okay, I'll do it.
So you don't need to do the Z-cut. I see the confusion. I should have explicitly say, I want you to repeat the same as FastQC for sample 2. Okay. Good point.
इस पर डायरेक्ट नहीं जा सकते क्या? इस पर क्लिक करने से तो ये नहीं मालूम दिक्कत कर रहा है.
Because this is data, na? This is data. This is not connected.
नीचे स्क्रॉल मेहनत करो थोड़ा ऐसा करना चाहिए.
दो लाइन का. So if we want to FastQC for sample 2, analysis complete.
Easy, right?
Yes.
Piece of cake?
कॉपी पेस्टिंग वेरी
if you want me to shut up and you do the exercise by your own, let me know. Any issues with the second sample? The quality looks like the same as sample one?
Results look basically the same as like what we got.
Quality
The quality of the quality scores drop at the end of read 2. Yeah, that was used to very common like a few years back, like 10 years ago. Nowadays the quality is great. Even what is how much you can push NovaSeq? The length of cycles. How many cycles you can push them? 600 cycles. So 2 by 300, for example, you could push them, and the quality drops. You know.
Actually, for the R2 read for 600 cycle, post say 450, 500 base pairs, it drops back.
Okay. So what causes the drop?
I think it's fluids and the heating of the sequences of the lab.
Okay. So we have an answer. 2 by 300 is the max we probably can push it. Although the quality will drop at the end. Yeah.
So now you guys actually, so you have a machine, they call MySync 100. They are just releasing a kit for 2 by 550 for the cycle.
Oh, okay.
2 by 300 means 300 cycles.
So they do read 1 first, and then read 2. So that's why the quality also drops in read 2. Well, Bonnie. So when you do paired end sequencing, when you do 2 by 150, it's 150 the first cycles and then 150 for the second cycles, or
Yes, so what happens is that actually,
for read 1 and read 2, I mean.
yeah, read one. So the first it will have read one primer and sequence from one end to another end
Yeah.
for 150 base pairs. Then it will sequence read one index and whatever index that you give. And then it calls flipping of flow. It actually flip the flow cell and then it will actually add the read two primers. And
So the cycle 151 is the first base of read 1, read 2, sorry.
no,
So no?
need not be.
No?
It's actually based on the insert size.
So if the insert size is bigger than
If the
150, it
insert
might be
size
read.
is
Well, yeah, of course. Yeah. But I mean, assuming that it's perfectly 150.
yeah.
Yeah.
So that will be added 12 or 13 depending upon the index base pair cell.
No. So suppose you have a 500 base pair insert. That means the first 150 base pair from this end will be sequenced. Another 150 base pair from this end will be. If your insert size is say 250 base pair, then first 150 will be sequenced from here. Another 150 from this side, which means you have an overlap of 50 base pairs into the read.
Yeah, but I'm talking about the cycles. The reason the read 2, the read 2 quality scores drop is because there are later cycles in the process.
Yeah. So it's a
That's what I meant, sorry.
So it actually affects the
No,
fluids.
cycles will be different, right? The number of cycles will be different. You are talking about the reading of 150 bases.
So number of how many bases are there? That is depends upon number of cycles. It's a cycle of image that you are taking. You can say like that.
One cycle is taking one.
It's the same. One base is one cycle. So the reason that the read 2 drops in quality is because they get sequenced later. So the machine is already wearing down.
So when it is 2x 2 into 150 matlab paired end reading and 150 cycles, right?
Yeah.
300 cycles from both ends.
From both the ends. And if it is 1x into
So
150,
here, on this technique, you are adding a reagent for 300 cycles. Okay. If you say machine that I want to do 300 cycle, it will just sequence from beginning to end 300 cycle. You can also say that okay, you do 2 by 150. You can also actually say I want R1 has 200 cycle and R2 has 100 cycle. So you can set the
Any
sequence the way
combination,
you
yeah.
want. The only thing is it will only do 300 cycles. And whichever way you want it to do.
Maybe if he said 150, maybe initial the reagent may not be there enough for the
Yeah, exactly.
another 150.
Yeah, he mentioned that there are different reasons why the quality drops. So next step 2, guys. So trimming, right? We check the quality is more or less okay. We can trim low quality bases. We can trim adapter sequences out of our sequences. So one tool that can do that is called FastSpeed. And one trick, if you don't know the arguments for a program, one thing you can do is just run, generally works, is run the program name without anything, giving no arguments, no parameters, nothing, and it would provide some sort of help, right? It tells you what it is. It tells you that if you provide some sort of dash I and an input, you're going to get something, etc., etc. So you could read the manual like this if you have any questions. So the next cells, what we're going to do is to trim sample 1, right? And we're trimming read 1 and read 2. Why I'm creating these variables? I'm doing it to make these more readable, right? So this command here is the same one as this one here, but it makes so long that it's hard to put it on the screen, and I thought maybe if I create variables, right? So I create a variable, the fastq variable, the fq here is storing the location for read 1. This is storing the location for read 2. And here I'm indicating the output, what I want it, and what name what I want to give it. So we are giving fastq files, right? We're going to produce fastq files too, without trim. So that's why I'm giving an output that indicates, oh, this has been trimmed, or somehow some indication that it's been trimmed, right? We are not modifying the original file. The original file stays as it is, and we're outputting something that is being trimmed.
How do we define how much trimming it requires?
Okay, that's a good question, saying how we define it. One thing is check the manual and look if there's a way to define it. So what I'm going to tell you is FastP is smart enough to figure out itself. So by using defaults, FastP does a good job. If you use Trimomatic, I think you need to be more specific and tweaking things. FastP trying to be a little bit smarter and do it by itself. It doesn't mean it's correct always, right? So always check it. But FastP, for example, all these tools generally have the Illumina adapters in it, incorporated. They have some database or something, and they compare it. So if it finds it, it removes it. It checks the quality and says, oh, these bases are low quality, let me remove it to something reasonable.
So Tribomatic is manual. So FastP is do it by automatic.
I mean, if you don't give, if you give 0 arguments to the software, just the input and the output, it does a pretty good job, yes. Think about it, all these programs, they already have defaults, right? If you say, oh, I want to remove anything that is quality scores below 20, you could input manually or check the default and see what is the default. Some of these programs already have defaults. So.
All these commands are also available default.
Yeah, they have. And in FastP, I recommend that you run it as it is. It's fine. I mean, if you see something weird, of course, you need to double check. So if you run this, it should trim, and it's fast. Well, I mean, we're giving it, there's a trick that I didn't mention. These files are not complete. They only have 100,000 reads. I don't know if you noticed. It doesn't have millions, so that's why it's going so fast.
So the initial two files over here, these are our inputs, out1 and out2, these are output.
Well, don't ask me. You printed the manual a moment ago. What you're asking me? You have it there. It tells you what it is.
So we have defined
This
the
is the
name.
location.
Yeah.
And FastP is the automatic. There we can define it.
Yeah, there are parameters you can tweak them, definitely. But as default, FastP does a really good job.
Trimmed file. Yes.
And trimming, it works, but if even alignment, get rid of things that are bad, right? So if you have do you remember that read that was repeated a lot of times? It was A, it's not going to align it anywhere. So even if the FastP doesn't remove it, the alignment process is going to take care of it.
So here the Q20 basic. So if we set the cutoff of Q20.
You know how many you remove.
So it's giving us options, right?
Well, it gives you a report, right? So it tells you how many bases are Q20 and above. So you have 95% are Q20 and higher, Q30 is 91 and higher, and there are 0 that are 40. So Q20, so you have 4 point something percent that are below 20. Those are probably the bad bases, yeah. It talks about duplication rate, it gives you a final report, right? It tells you how many reads pass the filter. So we started with 100,000 plus 100,000, that's 200,000, and we lost 3,680 after filtering.
Where can we see these trimmed files?
Sorry, what?
Where can we see these trimmed
HTML
files?
report. HTML report. Most
What file, sorry?
So final file.
Oh, the final?
File.
What is the final file? You should
So
know.
it's HTML format, right?
No, that's a report only. What is the trim file?
Trim file will be same.
It's the same folder, you indicated it.
Okay.
You indicated out and the location.
But it's not there. The sample trimmed. Trimmed, there's no sample.
Unaligned.
Trimmed.
Yes.
Trim dot fast queue.
Yep, that's the output. But it's true that the software also created a. Oh, my bad. Sorry, I didn't. It's true. It's not in the same folder. I forgot to tell you. This this function here created a new folder called trim. But you should know the location because you indicated here.
Sample one.
Yeah. So I wanted to keep them separated so it doesn't mess with the other one. So that's another common thing we do. We create another folder. And you have the HTML report, right? I don't know how it looks like. I don't think it's going to look that good because we're only working with 100,000 samples, but yeah, it doesn't plot anything. But any problems?
Just I want to know, there is like just to give reference to like fast command and fast command.
Yeah, you can give them at once because they need to keep the same. When it removes one read, it's going to remove the other one too. So you're not going to remove. So let's imagine read 2 is low quality, but read 1 is high quality. You're going to remove both of them. You don't want just remove read 2. You want to keep the pairs. So if you need to remove one of the pairs, you're going to remove both of them. So you need to indicate read 1 and read 2 per sample. Yeah, you indicate both of them at once.
What is showing the sample one?
And also it's a smart, right? And it creates two outputs. Okay, run for sample 2. Trim it. Remember to create a new directory called trimmed.
command, it should be one line, multiple lines are better. So that's another way to make it work. I didn't want to explain it now, but up with the title. That is, I'm telling you, this is a comment. I'm making a comment here that needs to take notes.
We have done the second sample.
Oh, actually, I explained what the forward slash means. I forgot about it.
Then we insert the head command.
Sorry, what?
Then we insert the head command. Head.
Questions? No? Oh.